Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Logic Simplification Examples Using Boolean Rules and Laws. Okay, at this point in your academic career, some of you guys might be keeping it in between the lines, and some of you guys might be choosing at this time to drive it off the cliff. Reason why is because the whole time I've been talking about this course is I've been harping on staying organized. And some of y'all have been wondering, hey, when is this going to get complicated? When do I have to stay organized? Well, that answer is today. It's going to get complicated today, and you got to start staying organized from now on if you have not been organized thus far. Okay, the reason why is because we're going to start applying those Boolean rules and laws we just learned in a previous lecture. To do this, though, I want to do in a kind of a stepwise fashion. Traditionally, using the Boolean rules and laws, the simplification examples don't occur until you've been introduced to De Morgan's theorem, which is a closely related theorem, and then they try to do these logic simplification examples. And people are easily lost because you're trying to do three things at once. What I'm going to try to do is do this in stepwise fashion. And like I said earlier, the only way you can learn these is by doing examples. So what I'm going to do is do a couple of simple examples using just the Boolean rules and laws before we go on to De Morgan's theorem, okay? Which is, again, a closely related theorem we have not discussed thus far. And one of the easiest ways to, again, illustrate these things is just do simple examples. And when you do these examples, stay organized. Stay organized right now, because it is super easy to get lost doing these things. And I'm going to give you guys some tips and hints on how to go ahead and stay organized. And the first hint to do this thing is what are the rules and the laws? I.e., have your cheat sheet ready. Have them written down in your cheat sheet. Have them readable and understandable so you can go ahead and apply these things. So let's go ahead and just write down all the laws and the rules. And I may have been previously misusing the terms rules and laws and properties. They're all rules. They're all things that you guys have problems obeying. Okay, show up on time. I got some problems with that. Just go ahead and write out your rules and laws we've discussed thus far, and here they are right here. There's our laws: commutative, associative, distributive. What's the commutative? A and B is equal to B and A. A or B is equal to B or A. Basically saying doesn't matter which order they show up in. Associative property for AND gates: B and C ANDed with A is equal to A and B ANDed with C, which we showed was equal to a triple input AND gate, basically AND them all together. For OR gates, same thing. A or B ORed together first, then ORed with C is equivalent. I should be using that triple equation sign. We'll just say equivalent. I'm not going to go back and do the other ones. A or B or C OR together and is equivalent to A or B or C. Distributive, finally, is B or C. And some of you guys may have caught that in the last one. I'm using the term factor and distributive, distribute interchangeably. That's wrong. I broke a rule. Sorry. Okay, I'm distributing that A within there. So that's distributing. Going the other way, that's factoring. So I did 100 push-ups as penance. Those are our laws. Those are easy. I'm not even going to write those things down. I'm just going to refer you to those. Let's write our rules down. What are our rules that we went over? Okay, and what I like doing with these rules is divide them up into groups of 4. So you got your AND rules, you got your OR rules, and your miscellaneous rules. And so the ANDs, they all start with an A. ORs, they all start with an A. ANDs all have ANDs, ORs all have ORs. What are you going to do? What are you going to AND something with? How about a 0? How about a 1? How about an A? How about a not A? What are you going to OR it with? How about a 0, a 1, an A, and a not A? Notice the similarities between them. It's easy to remember these things. The punchline is what are these equivalent to? And that was what last lecture was about. We've only discussed the rules. We haven't really applied them yet. A and 0 should be equal to 0. A and 1, A and A is A and not A is a 0. Go ahead and see if you can fill out the ORs. If you do so, you should look something like this. What are our miscellaneous rules? Okay, the first one is not A is equal to A. Also make sure, and the other thing too is take the time. I'm going to do this right here. I'm going to pause the recording, make sure I've got my rules written on my cheat sheet correctly, because nothing will mess you up like memorizing the incorrect rule. So make sure you've got the correct rule. Okay, looking good for these first 9. Well, we've got rules 1, 2, 3, 4. And remember what I said about the numbers. They're not necessarily interchangeable between schools of thought. 10, 11, and 12. 1 through 9 are kind of standalone rules, whereas 10, 11, and 12 are kind of derived rules based off of rules 1 through 9. So if you really want to be tough, you can kind of get by with just the first 9, but we want to make our job easy. A or A and B is equal to A or not A and B is equal to A or B. And finally, this FOIL A or B ANDed with A or C is equal to A or B and C. And what are the other rules that I talked about? The rules is don't get hung up about A and 0 equals 0, and then you get an expression that says B and 0 and you freak out. Well, check it out. It's the form of A or 0 has the rule equals 0. What I'm saying is start thinking of in terms of, you could do this, colored object ANDed with 0 is always equal to 0. And if you see colored object ANDed with 0, what's the result? It's 0. And that colored object could be an A, it could be a B, it could be a C, it could be a colored object. I don't care. However you think about these things, it's pattern recognition. The A's and the B's and C's inside these things, you can replace them with colored objects. You can replace them with squares, triangles. Highly recommend against circles, because you could think that they're zeros. I don't care how you remember these things. Just it's pattern recognition. So we've discussed all these rules. Let's apply them to a logical circuit. And someone throws this circuit on your desk and says, hey, build this. And your immediate thought is, oh my gosh, that's huge. We got 3 AND gates, 2 OR gates, 3 inputs. And now I'm going to have to do a multi-level logical circuit analysis of this. And let's just do it the hard way. What are you going to do here? I mean, pick those intermediate signals. Here's one right here. I'm going to call that D. Here's another intermediate signal, E. What's this guy? That's F and G. What's this final OR gate, X, doing? Well, it's saying X is equal to D or F or G. What's D? Well, D is A ANDed with B. What's F? Well, it's A ANDed with E. What's G? Looks like it's B ANDed with E. And so what I'm doing is I'm kind of going from the output back to the input. You can go from input to output however you want to do it. And now the next question is what's E? E looks like it's B or C. Start putting it back together here. What's your expression? X is equal to D, which is A and B, or F, which is A ANDed with E. What's E? B or C, ORed with G. What's G? G is B ANDed with E. What's E? B or C. And notice I'm using those parentheses because this is wrong. That's wrong. Okay, because G, the whole thing, E, the whole thing is this. So that is our final logical expression right there. And that would be a real pain. I mean, think about that visually. Think of all the wires you've got to make. You know, you've got one for A and B and C inputs. You've got to route that A input to 2 different places, the B input to 3 different places, the C input to 1. Then you've got to take the output D and go into an OR gate, the output F go into an OR gate, the output E has got to split up. And remember what I said is I'm talking about this spot particular here. You can always take the output of a gate and go to 2 different places. You know, I can feed several different inputs as long as it's within the fan out limits of that circuit. Fan out. Thus far I've been limiting our discussion in the digital electronics courses to black box. Don't worry about it. It's high impedance. There really are, and you'll learn about this in semiconductor devices and circuits, how the internal workings of these things are. There is an output current. There is an input current. It's extremely small. For that output to drive a large number of gates, it's not going to work because the fan out requirements. You can't go higher than 6 gates or 20 gates or whatever, because you got to keep it within that limits. But what I'm saying is this circuit it's complicated. It's purposely complicated, and it would be a real hard thing to go ahead and wire this thing up. I mean, think about from the terms of a motor control perspective, and we're going to have an entire lecture just on how digital logic principles are applied to motor control. What would the ladder logic for this thing look like? I'm going to go ahead and pause this thing and I'll just flash up a picture of what the motor control, the ladder logic for this circuit would look like. And there you go. That's the ladder logic equivalent for that circuit for us to light up that particular controller relay right there. And it's a nightmare. I mean, think about all those contacts and switches or push buttons, whatever A and B and C might represent limit switches or whatever. It's complicated to wire this thing up. What if you are capable of somehow reducing some of that redundancy and extra paths within there by simplifying this circuit? And that's exactly the purpose of using these Boolean rules and laws, is to go ahead and derive a substantially simpler logical circuit, i.e. this one, the actual connections of it, this motor control version of it, or even this expression right here. How do we simplify the expression if we were to go ahead and write this thing in Vhdl? It's purposes are threefold, is to simplify these circuits. And how do you do that is you apply those rules. So I'm going to go ahead and give myself some room, and I'm going to show you some of the tips and techniques I use to go ahead and simplify a logical circuit using the Boolean rules and laws. Okay, so all I did was just move this thing around and give ourselves a little bit of room. And like I said, it's have your 12 laws available. All I would do is just push them up to the top. What am I going to do first? And again, and I alluded to this in your previous lecture there, stay organized, leave yourself a trail of breadcrumbs. Don't do everything at once. Tell yourself what you're doing. Look at this guy right there and this guy right there. Do you think I can distribute that A in there? What about that B in there? What does our new expression look like? What am I doing? I'm distributing. Okay, in case I mess it up, I know where I'm at. Haven't done anything to that one. What's it look like when it's distributed? Okay, so you've got this new expression there. Do you see any particular occurrences for those rules? Do you think there's something that you might identify? And the order I do these things in, it doesn't matter. Okay, the order in which I apply these rules does not matter from here on. I had to distribute it to get it to a recognizable point to start applying these rules. But if you see one of the Boolean rules and laws before I do, and you apply it before I do, ultimately you're going to get to the same expression that I get to at the end. So what I'm going to do is I'm going to see this one right there, B ANDed with B. And you're going to look through your 12 laws and say, hey, I don't see anything with B ANDed with B. And the answer is, guys, come on, be more flexible. What about rule 3? Something ANDed with something is something. So I'm going to say rule number 3, so B. I'm simplifying that thing down. Again, I'm doing one step at a time. What else out there might you see for our rules? I'm going to look at this guy. Look at that. You got two duplicate things being ORed together. What about rule number 7? Duplicate ORed with duplicate is that original single value. So I'm going to say number 7. I can simplify that down to just AB. Look around for another pattern. What about this guy right there? Something ORed with something ANDed with something else. That looks like rule 10 to me. A or A and B is equal to A. What about B ORed with B ANDed with C? Okay, what can I simplify that to? So number 10, that's going to simplify down to B. And like I said earlier about number 10, 11, and 12 kind of being derived rules, if you want to be tough, you don't have to remember those ones, because check this out. I can always, here's the tough guy root, I can always factor out that B, 1 or BC. So I've factored it. What do I do when I factor? Well, 1 ORed with something, what am I doing? I'm applying rule 6. And now B ANDed with a 1, applying rule number 2. I get B. Ultimately, you're at the same result, B. Whereas with step 10, I can immediately go from there to there. Whereas if you want to go the tough guy route, you got to apply, you got to factor it, you got to do number 6, then you got to do number 2. Ultimately, you're going to come out in the same place. What am I doing now? Okay, maybe there's another occurrence that I could somehow simplify this thing. And it may not be immediately recognizable because of the spacing of these things. Well, we've used the distributive property. Maybe we could use the commutative property to go ahead and swap this thing around and see if you recognize a pattern. What if I said, okay, I'm going to remind myself, what am I doing? Commutative, rearrange. Not even going to spell rearrangement. What if I swap that B over there? So I commutative rearrangement of the whole thing. B or A and B or AC. Doesn't this kind of look like another occurrence of rule 10 there? And what does that simplify to? That's going to be B or AC. It looks like that whole gobbledygook, which we had right here, can ultimately be simplified into the following expression right here. And some of you guys might be like, are you a wizard? No, I'm organized. Okay? All I did was use those rules, and I told myself every single time what I'm doing in the steps, and I come up with a simplified expression. And the results of our simplified expression are substantially easier to, number one, write out. And how much would it bet if it's easier to write out? It's a lot easier than hooking up this thing. And if I had to do a motor control scheme, it's substantially easier to hook up than something like this. And if I had to write a Vhdl program, it's probably easier to write that expression. So let's go ahead and see what, go ahead and take the written expression here we came up with. X is equal to B or A and C, and do a traditional schematic in logic gates. If you can do the motor control thing, I know I haven't discussed it yet, try it out, and then just see if you can write up the Vhdl expression. So here's kind of our scheme that we want to do. This is our original on the left-hand side, our original written expression, our original motor control expression, our original logic schematic diagram expression, and on the right-hand side, here is our new simplified written expression. Okay, so let's go ahead and see if we can fill out the new motor control expression, the new simplified logic circuit diagram, and they're going to look like this. There you go. Okay, so the motor control ladder logic has been substantially simplified. Think of all those wires you've saved. Think of all the time you've saved. Think about this thing here. The smaller number of gates, the less power is being consumed, the less connections you got to do. And in the sake of completeness, let's go ahead and what's the difference between the original Vhdl expression and the new simplified Vhdl expression. So go ahead and see if you can write this in Vhdl, see if you can write that in Vhdl. Okay, so here's our original Vhdl expression. Look at all those parentheses in there. Look how confusing and how long that is. Compare it to that guy right there. Just think how much faster it is to type that thing. Think about how much more time in the parking lot you'll have to smoke your cigarettes. Okay? Just think about how easy it is to read. Compare those two. Okay? It's the simplification of these things. Like I said, it may not have happened the first time through, but if you want to go back through this same example again, just rewind it, check it out. I'm staying organized all the way through. Let's do a monton of examples because this is the way you learn these things. And by all means, go ahead and pause these recordings. Go ahead and see if you can kind of derive the same expressions I'm ultimately getting, and kind of use this as a guideline, as a handrail as you go through some of these examples here. Okay, let's go ahead and move on. Let's wipe this whole thing out and do another one. Okay, let's go ahead and try example 2 or example 1.0 if you will for our logic simplification examples using just the Boolean rules and laws. And what you're going to do when you go out in the woods to poke a tiger in the eye, you bring along your eye poke and stick. Well, what you're going to do when you're using your Boolean rules and laws, show up with the Boolean rules and laws. Okay, so have your list all written and ready to use. And this is the expression we've got. Someone has given you this. X is equal to, parentheses, A and not B, parentheses, C or B and D, parentheses, or not A anded with not B, parentheses, C. I mean, just think how long it took me to even say that expression. I'm going to go take a nap. I bet there's a way of simplifying this. What I'm going to do is I'm going to do the distributive property first. Let's work with these. There's a couple ways to tackle the distributive property. Let's start with this one right here. Again, I'm giving myself my next step. What did I do? I distributed. What I'm going to distribute is that A not B term into that internal set of parentheses. So it's C, A not B, and with B, D, and I'm keeping everything else the same. And I know that you see something right there. Yeah, something sticking out of you. We'll get back to it. Trust me. Trust me. What am I going to do now? I'm going to distribute the whole thing again because I've got this larger parentheses. I'm going to distribute that C into there. Okay, check your work. And what did I do? Distributed. And go ahead and see if you can recognize some occurrences of those particular rules. This guy is pretty glaring right here. C ANDed with C looks a lot like rule number 3. Okay, so it sounds like I can get rid of that duplicate term. Again, I'm only doing one step at a time. I know you're tempted to do some of these other things. What's the next glaring one? Is that not B ANDed with a B? That looks a lot like rule number 4. So I can put a 0 in place of that not B ANDed with a B. Everything else stays the same. Okay, when I AND something with a 0, that to me looks a lot like rule number 1. The whole term that it's being ANDed with is a 0. These other guys are unaffected by that. Now, what am I going to do? Well, something ORed with a 0 looks a lot like rule number 5. Go up, give ourselves some space up here, all the way up, give ourselves lots of space. So I'm saying number 5 gets me to the spot here where it's just A not B ANDed with C, or not A ANDed with not B and C. You may think, okay, that's as far as I can get for these rules, but think about, you got some common terms in there. Think of the term not B and C. Not B and C. Okay, what if I factor that out? Not B and C. What am I doing? I'm factoring. Because if I was to distribute this, I would go back to that. Do you see what I'm doing? Factor is the reverse of distribution, vice versa. So now what happens here? What's A or not A? That looks like a lot like a rule number 8 to me, doesn't it? I'm going to say number 8. Finally, what do you get when you AND something with a 1? That's a rule number 2. Not B, ANDed with C. That is our final simplified logical expression. We went from this giant thing with parentheses and 4 terms all the way down to a single AND gate and a single NOT gate with only 2 inputs. Ultimately, what would this thing look like? Well, it's ANDing the terms B, well, it's ANDing not B and C, output X. What about inputs A and D? Don't need them. Get rid of them. Don't even put them in your circuit. Talk about simplification. Let's move on to example 3. Okay, so let's try example 1.1 here. For a logic simplification example is using just the Boolean rules and laws, and someone throws this nightmare upon your desk. It looks like you've got 4 inputs and their complements, A, B, C, and D, all feeding 5 AND gates, all feeding this mothership of an OR gate. And what is this? Well, it's a SPLD. It's a simple programmable logic device. It is a programmable AND array, all feeding a fixed OR gate. How does this diagram work? Well, it's a one-line diagram, one-line notation, and those particular AND gates have a number of inputs. It could have up to 8, it could have 6, I don't know what it is, but those connections, those X's, that's what those AND gates are getting. Looks like that first AND gate is getting the terms not A, ANDed with not B, ANDed with not C. The second AND gate, the third AND gate, the fourth AND gate, the fifth AND gate. So go ahead and see if you can figure out what those expressions are. You should get these. Okay, so the first one again is not A, ANDed with not B, ANDed with not C. The second one is not A, ANDed with B, ANDed with C. Third one is A, ANDed with not B, ANDed with not C. The fourth one is A, ANDed with not B, ANDed with C. And the final one is A, ANDed with B, ANDed with C. What are they being done to them? They're all being ORed together. There has got to be a simpler way to write this expression. How are we going to do it? We're going to use our Boolean rules and laws in a systematic manner and go ahead and see if we can find some ways to simplify these things. I'm actually going to go ahead and erase the PLD diagram here because we're going to need a lot of space for this one. Okay, so there are 5 AND terms and they're all being ORed together. This is where organization becomes key, and your ability to stay organized, keep track of what you're doing basically, is because it is super simple to potentially forget a NOT gate or forget a OR AND term as you're doing these things. It helps to have these things written out. Brief moment though before we actually begin this thing. We're going to come back to some of these expressions for next unit's lectures. This is an SOP expression. It's a sum of products. It's a bunch of ANDs feeding an OR. What do these represent? Combination 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, triple 1. Okay, ignore that for right now. We'll come back to this for Unit 5 SOP expressions and simplifications. How am I going to get this to Boolean so I can use the Boolean rules and laws? Make use of the commutative property. You can always rearrange these things, and it's a little bit of an art form to kind of recognize terms. You're going to kind of make it arrange it so you can use some of these laws. What I'm going to do is I'm going to see this one. It got a not A ANDed with B and C. Look at this one. I got A ANDed with B and C. There's a common term there. But I'm going to kind of push those together. So I'm going to say commutative. I'm just going to rearrange it so I can put these guys next to each other. And you'll see what happens here. Not A, B, C. ORed with A, B, C. The rest of the guys do the same. Have I copied them correctly? Looks like it. Okay. Yes, okay, I've copied it correctly. What have I gained by doing this rearrangement? Well, remember I was talking about there's a common term in there. What is that common term? It's B ANDed with C. And if I take that out, if I factor that out, look at that. I'm setting myself up for one of those Boolean laws. Again, what have I done? I've factored. Which ones have I factored? I factored this one. What have I done with the rest of these guys? Nothing. You don't have to do this one first. I know there's another one that you could factor out, which we'll do a little bit later, but I'm just doing it step by step. That's our Boolean law. Which law is that? That's number 8, which says that that is equal to 1. What have I done with the rest of these guys? Nothing. They're just hanging out waiting for their turn. What is something ANDed with 1? Well, according to rule number 2, it is B and C. What have I done with the rest of these guys? Nothing. I had to rearrange that one to use the factoring number 8 and number 2. I've got everything set up for you to do the exact same thing for this expression which we just yielded right here. See if you can find another spot where there's some common terms that you could potentially factor out. And I'm telling you, it's got rule number 8 in it. And then you're going to use rule number 2. So where in this expression in green can I potentially factor out use number 8 and number 2? The answer is right here. Okay? Because A and not B is common to both terms. So let's go ahead and factor out A and not B, not C or C. I'm setting myself up to use rule number 8 again. And see what I say? It could be so easy. It could be so easy to accidentally, see the error that I made right there? It could be so easy to forget a not term. So it helps to have these steps written out. What am I going to do? Do number 8, that's 1. And I can apply rule number 2, again to simplify that. Anything else out there that you might be able to simplify or rearrange? What's the error, guys? Look at that. I like to say I was just testing it, but I really did make a mistake there. So again, it helps to compare what you started with. Maybe I could use the commutative property again. Kinda, if you're not seeing what I'm seeing here, we might be able to rearrange things. I'm gonna say commutative. Maybe I could take this term and this term, kind of stick them together. What I'm getting is this. What I have is a common not B term. So I'm gonna factor that out, not A. End it with not C, or A, or BC. Okay, so now this is what I'm talking about is being flexible. Where can you see a pattern in here equivalent to, I know it's not using the exact same letters to our Boolean laws, and what I'm referring to is this one right here, excuse me, Boolean rules, is that one, rule number 11. It's the hardest one to kind of recognize. It's A ORed with not A and B. It's kind of equivalent to this because I could rearrange this as, so your ability to use that commutative property, and again, be flexible. I know it's not a B, it's a not C. What I'm saying is it's an original logic value ORed with its complement and something. What does that yield? Well, it's going to be, according to rule number 11, that not B stays the same, should be equal to A ORed with not C. All the rest of those guys stay the same, and now I can kind of distribute not B in again. You can leave it at this one here, but you want to go to kind of the SOP expression with ends of ORs. So I'm going to distribute not B ANDed with A, or not B ANDed with not C, ORed with B and C. If you want to stay in alphabetical order, I don't know why, but your expression has gone from 5 3-input AND gates down to 3 2-input AND gates. Substantially easier to hook up, and in the case of SPLD, substantially easier to write the Vhdl expression, which would look something like this. There you go, we could do this in stages here. A and not B, ORed with not B and not C, ORed with B and C. Think of all the highlighter colors I'd have to use to do that guy, how long that expression would be. That was a pretty complicated example, but it is we're going to be using this a little bit later when we try to do simplification of SOP expressions. And okay, let's just go ahead and do another example 4 here. So let's bring this home with one more illustrated example. Example 100, example 4. It's a pretty cool example because it shows you, and there are many different ways to do this, but ultimately if I'm applying these Boolean rules all the way through, regardless of the order in which I apply them, I should get the same result. This is it's pretty neat because some of you already recognize there is a drastic shortcut to this, and then some of you may not see this readily apparent in there. What I'm referring to is rule number 8. One may think that I might have to use the FOIL, the methods of distribution, but look at this guy right here. I already see rule 8, which is A or not A. Something ORed with its complement is always equal to 1. I could drastically simplify that, but I don't want to do that right now. Okay, I'm purposely illustrating that there are more than one ways to depilate a feline. Okay, here, to skin a cat. I'm purposely going to complicate this, and I'm going to FOIL everything. Let's say I go insane. I totally forget that rule 8 exists. What I'm going to do is I'm going to do the first A ANDed with AB. The outer, A, ANDed with A, B, not C. The inner, not A, ANDed with AB. The last, not A, B, not C. So what have I done? I've done the FOIL, which is just got to spell it correctly, which is kind of like distribution. Are there any things in here that you can recognize as some of the Boolean laws? Well, right there, that is rule number 3, AB. What about right here? Rule number 3. What about this? Something ANDed with its complement. That's number 4. What does 0 ANDed with something? That's kind of rule number 1. What does something ORed with a 0 mean? Well, that's rule number 5. It's like I can get rid of that 0, and I know there's shortcuts within here too. Okay, what's the next occurrence here? Probably that guy right there. That is something ANDed with its complement, i.e. rule number 4 again. And that's going to bring us all the way up to the top. What's this guy? That's number 1. What about rule number 5 again? Now I could potentially factor out the like term, okay, because AB is common to both of those. What's that guy right there? 1 ORed with something. That's number 6, AB. So this is an incredibly long way if I started out without FOIL. That's 1 step, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps to get to the answer, AB. I'm going to put this over here at the side, because watch this. Let's start off with rule number 8. If we started off with rule number 8 right here, if we did recognize that at the onset, we could substantially simplify the simplification. Let's try that. Okay, same expression. However, we recognize the onset that that is number 8. That will simplify to 1. Everything else remains the same. And if we treat the terms inside the parentheses as a single unified expression, which it is because it is in parentheses, what we get is something similar to rule number 2, which states that that can be simplified as AB or AB ANDed with not C. There's a common term, AB. Let's go ahead and factor. And we're left with something for rule number 6. That's 1. Something ANDed with 1. Number 2, AB. Oh my gosh, we have the same answer in 1 step, 2 steps, 3 steps, 4 steps. Where you apply these things can sometimes shortcut you to the same answer. Ultimately, you should get the same answer. Sometimes it just may take a little bit more work. That's what I'm saying is keep these steps here. You may recognize a shortcut later on. You may have to go back to it, but ultimately you should be getting the same answer. This kind of concludes this portion of the lecture. As a parting gift, though, I'm going to give you guys some things to work on. Here are 4 expressions using just the Boolean rules and laws. We should be able to go ahead and come up with the answer for these. Okay, so expression 5, W is equal to B and C, or not B and C. Just read through these. I'm not going to read them out for you. Try to do it yourself, okay? Because pause the recording, because what I'm going to do is I'm going to give you a hint. Okay, if you can't, try to do it without the hint. And if you can't do it, try to do it with the hint. Okay, and ultimately you should be getting the answers that I write down. Okay, so here I'm going to go ahead and write down the hints. So try 5 by yourself, try 6 by yourself, 7 and 8 before you look at the hints. Okay, so here's the hints. And again, you should be trying these things prior to looking at the hints. You don't have to use these hints. You don't have. There's other ways of doing it. For example, number 5, I'm going to factor out a like term. There might be a like term in there you could find. Then I could potentially use number 8, and then I could potentially use number 2. Same thing here, same thing there. And ultimately, you should come up with the following answers. There you go. So there's our answers. Hopefully, you arrived at these expressions. And notice the hints. I haven't given you all the hints. That's the purpose of a hint. I'm not telling you what terms to factor out, not telling you what terms to distribute, but ultimately you should come up with those answers. So this has been a couple worked out examples of logic simplification using just the Boolean rules and laws. You know, this is not easy. This may be you right now. Don't worry about it. The first time through is a little confusing. All you got to do is stay organized. Have those expressions written. See if the more you do this, the easier it becomes. Okay? So now we're actually going to go on to the kind of the third step. We talked about the laws. We talked about the rules using simplification. Now we're actually going to go ahead and introduce De Morgan's theorem. It was an incredibly useful theorem for Boolean simplification, and then we're going to combine them all together. We're going to use the rules, the laws, the properties, and De Morgan's theorem to go ahead and simplify logic expressions.